Hello, this is the module on math review and the production possibility frontier. There'll be 3 different videos. This is number 1 of 3. On this video, we'll have a short math review of the types of math you need to know for this class in economics. And we'll cover what a slope is, how to calculate it, a little bit about correlations and using regression analysis, and something about causality. In the next video, we'll go over the PPF, the production possibility frontier model, and what is opportunity cost, what is diminishing returns. And then in the last video, video number 3, we'll go over the production function, and then a little bit about an example using this production possibility frontier model with 2 goods, investment and consumer goods. Okay, so first is a math review. And frequently in economics, I'll say something is a function. Consumption is a function of income, or investment is a function of interest rates, something like that. And the general form for a function is y equals f of x, or y is some function of x. X is the input and y is the output. So consumption might be a function of income. It might be a function of income and wealth and so forth. Without actually writing out the exact equation for it, I'll just say it's a function of these things, whatever that equation might be. One type of a function is an equation for a line. And in general terms, we write that as y equals mx plus b, where m is the slope and b is the y-intercept. So for example, I could write y equals minus 2x plus 4. It's the equation of a straight line where negative 2 is the slope and 4 is the y-intercept. I want you to be able to plot that and calculate the slope of that from that plot. The easiest way to do it in plotting this is just pick a couple of values of x, plug them in the equation, see what y is, and that'll give us some points to plot. So let's plug in 0. If we plug in 0 for x, y is 4. If we plug in 1 for x, that will give 2 for y. And that's all we need to plot this. We could have another one just for fun. We'll make x is 2. And if x is 2, that means that y would be 0. Now to plot this, by convention, we put the dependent variable on the vertical axis and the independent variable on the horizontal axis. Now in this case, y is the dependent variable because it depends on x. X is the independent variable. We pick any x we want, and then y depends on whatever we picked for x. So if we plot this, the first point is 0, 4. So on here, I'll try to put 1 point is right here, which is 0, 4. Another point is 1, 2, which would be right here. This will be 1, 2. And that's all we need. We'll draw a straight line through these. And if I do it right, it's going to look something like that. And you can see there the slope is negative, it's pointing down, and the y-intercept is 4. It also passes through this point to 0 if I've drawn it right. Now the slope is the rise over the run. Or the change in y over the change in x. So the change in y is going to be this distance here. This is the change in y. And the change in x is this distance here. I'll use the little delta symbol for change. So we can write that as the change in the y's would be 4 minus 2, and the change in x would be 0 minus 1, and that is going to be minus 2 over 1, which equals minus 2, which we already know the minus 2 would be the slope. So the slope is negative because it's pointing downward. So a negative slope points downward, and a line that's even steeper is even more negative. A positive slope is the line is pointing up, and if it's steeper, it's even more positive. If the line is horizontal, that is a 0 slope. And if the line is vertical, the slope is undefined or infinity. Draw that with the lazy 8. Now, if we're talking about a curve, then the slope is constantly changing. And usually in economics, we're using curves. A typical curve in economics might look something like this. Which means that the slope is constantly changing. We calculate what the slope is at any point on the line. For example, right here, the slope on that curve at that point is equal to the slope of a straight line that is just touching it. It's just tangent to that point. So if we were to draw a straight line here, the slope of that straight line is the slope of the curve at that point. So we can calculate the slope right at that point. We can see it's positive. And as we move along at that point, you can see that that straight line that just touches that curve is not as steep anymore. So the slope is still positive, but less positive. When we get up to the very tip top, the slope is 0. And as we start to go down, it becomes negative. So we start to head down, and then you can see that that straight line right about there becomes negative. And as we head down, it becomes more negative. Something like that. You can see that straight line keeps becoming a little more negative as we head down. Another line I want you to be familiar with is a ray from the origin. And a ray from the origin is just a line that comes right out from the point 0, 0, a straight line. So this is a ray from the origin. And a particular important line that I want you to be aware of is one that's called the 45-degree line. And that line is one that has an angle right here of 45 degrees. It's also where the slope is 1. The equation of this line is y equals x, meaning the slope is 1 and the y-intercept is 0. That means at any x value we pick over here, say 50, if we go up and we hit this line and come over to the y-axis, it will have the same value, 50. So this is a slope equal to 1. Now, correlations can be positive or negative. And in economics, we're always looking for correlations, variables that are correlated somehow. So if we go get some data, and it turns out that the two seem to be correlated, in this case, they're positively correlated. It means that x goes up, y goes up. So this is a positive correlation or positive association. If the relationship is this between x and y, we can say there's a negative correlation or negative association between x and y. Now, when we go out and we look for data, the data never falls on a straight line like that. If we're very, very lucky and we go out and we look for some data and plot it, maybe it will look like it's got some positive association to it or positive correlation to it. But it definitely won't be falling on a straight line. So maybe it'll look like something like this. And when you look at this data, you say, well, it does kind of look like there's a positive association or correlation between the two. This is known as a scatter plot, where we just plot the data on a graph. And what we want to do is try to draw a line that approximates what this data looks like. So we'll draw a regression line. Or a best fit line through this data. And without getting into exactly how that's done, there's algorithms for computing it. We can have the computer do it pretty quickly. And it'll draw us a line, some sort of best fit line that will approximate the data. Then we can look at that line and say, well, looks like there is some positive association between x and y. Of course, there's outliers that don't fit on this line, and some are way off. But in general, it looks like there's this association between x and y. It doesn't mean that x causes y necessarily to occur. It might cause y to occur. Maybe x does actually cause y to occur. But just looking at this, we can't say that's for sure. All we can say is there's an association between the two, whatever it might be. So in economics, we look for correlations all the time in the data to help support some sort of theory or hypothesis about what's going on. So we might say, well, we've got this idea that Studying for an economics test helps improve grades. So we go out and we look for some data. We talk to some people taking an economics test and say, well, how many hours of studying did you do for this exam and what grade did you get? We start plotting the data. So hours of studying for the exam would be the independent variable. Hours of studying, put that on the x-axis. Scores on the exam would be the dependent variable. So I think that scores on the exam are some function of studying for the exam. And we think maybe there's a positive correlation between the two. So we go out and we get this data, plot it. Once again, it's not going to fall in a straight line. There's going to be some people up here. They don't study at all, and they get a top score. And then there's going to be some people down here that study a lot and don't do very well in the exam. Maybe they don't take tests well, or maybe it's just not their subject. It just takes longer for them to learn, or maybe they've never had it before. But whatever the reason is, we would think that maybe studying does help on the exam. It does. There's some causal relationship between studying and exam on the scores. Well, the first step to see if that's true is to collect some data and run a regression and hope that the regression line is positive. There's a positive slope to it. So we run this and say, yeah, there's certainly outliers, but it does look like there's a positive correlation between the two. Now, this doesn't mean for sure that studying for an exam helps the exam score, but it does lend some support to that idea that hours of studying, more studying, increases the score on the exam. So it might be that X causes Y, but we can't say for sure. And why can't we say for sure? Well, there's some things that might interfere with that. For example, let's say that we go out and we get some data on some city in the northeastern part of the United States on their weather. And we get snowfall. We want to see if there's how much snowfall, and we want to see if ice scrapers are related to snowfall. So we measure the snowfall, put that on the y-axis. We measure the sales of ice scrapers. And if you don't know what an ice scraper is, that's good. If you live in a city where there's a lot of snow, when you get up in the morning, if your car is outside, there's ice on the windshield, and you can't see through it, and you got to get the ice off. You're not supposed to pour hot water on it because it can crack the windshield. So you have to get out there and scrape the windshield with an ice scraper to get the ice off before you can go anywhere. And of course, it's freezing outside while you're doing that too. Okay, so let's say we gather this data between sales of ice scrapers and snowfall, and we get a positive correlation between the two. Now, you know that sales of ice scrapers, the number of people buying ice scrapers, don't cause a snowfall. You know it's the other way around. Snowfall has got to be causing the sales of ice scrapers. This is known as reverse causality. X isn't causing Y, Y is causing X. Or in some cases, X might be causing Y and Y is causing X too. It's very difficult to say because there's some reverse causality going on. What if the sales of ice scrapers happened before the snowfall? Like one day before the snowfall, ice scrapers sales go up. Now, does that mean that sales of ice scrapers are causing the snowfall? No. Probably people are getting some information about snowfall that's coming and going out and buying ice scrapers. So just because X happens before Y happens still does not mean that X causes Y to happen. An example of this is the 1990s. Criminologists were trying to see if police had actually reduced crime, and to see if you added more policemen, crime would go down. So they did a lot of regressions. And on the dependent axis, they put crime. And they tried different types of crime. And this is usually done by, per 1,000 inhabitants. So per 1,000 persons. And on the x-axis, they put the number of police officers. So number police officers over here. And this is usually done the same way. It's like per 1,000 people. So per 1,000 persons. And they expected to see regression showing as you increase the number of police, there would be less crime. So they thought they would run into some regressions like this, negative association between the two, but they didn't. And there were a number of studies on this. It was hard for them to get this result. In fact, one journal article at the time did a summary, and they said that in 1996, there had been 78 studies. 78 studies using regression analysis where crime was the dependent variable, and only 14 of them got results where the slope was negative here, negative association. They actually had more than 14 that were positively associated. Showing, boy, as you increase the number of police officers, there was more crime. Most studies showed nothing, just flat, no correlation between the two at all. So what was going on here? Reverse causality. So crime was affecting the number of police officers. In the higher crime areas, higher crime cities, they put more police. So the police officers are being affected, number of police officers, by the amount of crime. But also the number of police officers were having an effect on crime too. It was very difficult to sort out what was going on here because of some reverse causality. Eventually, an economist did some studies with some pretty fancy econometrics, which is really just regression analysis for economics, and managed to tease out the data and figured out, yes, actually, indeed, there was a positive correlation between the number of police officers, or negative correlation between the number of police officers and crime, and showed, yeah, as they added more crime, as it added more police officers, the crime did go down. Another problem that is run into with this regression analysis is omitted variables. So, I'll put this down, omitted variables. So it might be that X and Y are positively correlated, but there's some other variable. We'll call it Z that we didn't think about or include in our research that affects both of them. So Z affects Y and Z affects X. So Z goes up, Y goes up, and when Z goes up, X goes up. So it appears that every time X goes up, Y goes up, and Y goes up, X goes up. They're correlated, but there's no causality whatsoever between X and Y. There's this other variable out there, Z, that's affecting X and Y. An example of this would be looking at distance from the equator and income. As it turns out, countries that are further away from the equator have higher levels of income. If we look at GDP per capita, which means output per person, we'll get into that later in another lecture. Here's a map of the world. Essentially shows the richer countries, who's richer and who's not. The light green areas are the wealthiest. Then the dark green areas, then these gray areas, then the brown areas. And if we draw a line through the equator, so the equator should go through Ecuador, right? So right about there. Should go through right here, right about Singapore, pretty close to the equator. So I'll connect these two, and there's the equator. And take a look at where the rich countries are, the light green ones. They're further from the equator on average. Look at Europe, look at the US, look at Australia. There's a few close to the equator, like Saudi Arabia, but not very many. Japan's kind of far away. Then look at the poorer countries and see where they are. A lot through Africa, or through Indonesia, and they're closer to the equator. So what's going on? If we were to run some sort of regression, and on the x-axis, we put the distance from the equator, and income per person. Up here on the y-axis, we get some positive regression, positive line here when we run a regression. So what's going on here? Does it mean that the distance from the equator causes countries to be wealthier? Maybe. Could there be some reverse causality? No. We can rule out reverse causality here because a country's income can't change where they are in the world. The countries are pretty much fixed with their locations. And if they become wealthier, they can't move to another place on the map. So reverse causality is out, but there might be something else going on there might be some omitted variable, something else. Something else might be going on here that is correlated with the distance from the equator and correlated with income. Sometimes I give my classes questions to do in class, kind of like a iClicker. Show questions in the class and they can pick the answer. And sometimes for extra credit. And I wanted to see one quarter if it was actually doing any good. Was it giving the students, was it helping the students learn? Was it helping them get better grades or not? So I got the data on a large class and looked at people's grades and then looked at how much they used this. It was a web-based Top Hat was called for answering questions. Ran a correlation. And the students actually got some extra credit points depending on how often they used this. They used it all the time, they got 5 points. They didn't use it at all, they got 0 points. And then I put this data into Excel and plotted it. So I had data on each student, how much they used this Top Hat, like this iClicker, for answering questions in class, and what their total grades were in the class. Ran a regression on it and found out that the slope was positive on it. Now that doesn't prove that using this interactive question and answer in class helps people's grades, but it does lend a little support that it might. The average grade on people that didn't use it at all was 245 points for the quarter. The average mean score of students that used it all the time was 270 points. But there was 5 points of extra credit that they could get for using it. So I subtracted that off, and the difference was 20 points, which was 6.7%. About 2/3 of a grade point on average between people who didn't use it at all and people who used it all the time. Could there be some reverse causality going on here? Yes, because maybe the people who get good scores went ahead and used this Top Hat interactive response system to participate in class. So maybe it's not that the response system of Top Hat improved their grades. Maybe it was just reverse causality. It also might be that there's some omitted variables here. Maybe there's something else that causes the better grades, not the use of this interactive response system. For example, attendance. In order to use this interactive response system in class, people had to come to class. So maybe it wasn't the the interactive response system of Top Hat that was getting people the higher grades in class. Maybe it was just the attendance that was causing them to get a better grade. And Top Hat was just picking up that information. That's the information I could get. So this doesn't prove anything, really, but it's a first step. If I didn't get a positive correlation here, I would just ended it right then and said, okay, this isn't going to help any. It's not going to help people's grades. Forget it. But since I got a positive correlation, it gives some evidence here that it might be helping. I would have to do a lot more to try to look for some more evidence that the two variables are correlated. But I chose to just stop there, and that was enough for me. Okay, on the next video, we will go over the production possibility frontier, which is an economic model.